Finish those off. And we're ready to move on. It's supposed to be crazy weather this evening, right? That's what I'm hearing. Pardon me? Oh yeah, it's going to be like late at night. That's yeah. Maybe they'll cancel school tomorrow. All right, we're ready to move on. 7-4. I don't know if any of y'all have noticed, but this is pretty much the point in the class where my lecture notes online no longer appear. Like there aren't any more lecture notes online. And it's really because of the nature of what we're going to do now. There's not a whole lot of notes that need to be put up. So, I might provide you with some resources, but I'll just hand them out in class. This, as you'll see, isn't going to require much, all right? We're going to come up with this concept of what's called Arclength. And remember, the underlying theme of this entire chapter so far has been using the integral to add up things, right? And the integral, we just need the integrand, the part inside, is just the formula for what we want to add up, right? Whether it be areas or volumes of solids or shells or cross sections of some weird solid, right? All of it's just a formula inside. So arc length. Let's just take a function, just your regular old function of x here. Back in college algebra or calculus 1, we've got some functions sitting on a piece of paper. And what we're interested in here is if we could take this thing off the page. So imagine that this was like a rope, okay? And I could take it off the page and straighten it out, right? Can I borrow your charger cable?
It's a little broken.
That's okay. I'll break it some more. That's all right, though?
Yeah.
Okay. So if we had this right here and we were able to somehow take this frayed fire waiting to happen cable, right, and take it off the page and then straighten it out and measure it, then, how long would that be? That's the arc length. Pretty simple concept, right? Yes? The idea of what we're trying to do, that's pretty straightforward. So our question is, how long is that? Well, one thing we could do, right? One thing we could do is we could approximate it. We could imagine creating a right triangle here, connecting these 2 points with a hypotenuse. And that hypotenuse would be an approximation. We would be way off though, right? Yeah? So how could I get a better approximation? Yeah, why don't instead of me using one triangle, why don't I cut this thing, okay, cut it into 2 equal sections, do this triangle, and then do a little triangle right there. Do y'all see how that's probably going to be a better approximation? Or no, you're not happy with it? Well, it's not a triangle unless you extend it over, then it would be a right triangle, right? I could get that to be a triangle. Yes, I agree it's not. It's a trapezoid or something, but you get the idea? Okay. And then I could try and go even better by maybe 3 or 4. Maybe I do, a couple of these and start connecting here to here, and then 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 here to here. And each one of those, I could create little right triangles on each one of them. Yes? Okay, and then wherever that one would be, I don't know. And then here's a little right triangle in there. and there's a little right triangle. So if I were to get all the hypotenusae, what is the plural of hypotenuses? Hypotenuses? Hypotenusae? I don't know. Get the hypotenuse of each one of those, right? Add them up, and that would be a better approximation than that one, wouldn't it? Yeah. And what would be the exact arc length? If I cut this up into an infinite number of them, right? And that's exactly what we were doing when we were doing areas, right? We were coming up with infinite cuts. So really, I need a formula that represents the hypotenuse of one slice, okay? Just the hypotenuse of one slice, and that's what I'm going to try and create here. All right, so let's start over here. Go back to this. Start this thing over. I mean, the integral is amazing in this way. If you can just come up with a formula for what you're trying to represent, then you can add up all these pieces. So I'm going to take some arbitrary slice. So a slice means I need some sort of width here, which would probably be called, I don't know, dx, right? And go up here. That'll hit 2 points, and I'll create a little right triangle out of that. And, well, that's too hard to see, so let's just blow that thing up, okay? Let's just zoom in on that and take a look at what we've got here. We've got some curve doing something in here. We've got a right triangle that we've created, and the hypotenuse that is right here. And yes, there's some error, but as I let this thing go to the width of this become infinitesimally small, the error basically vanishes away to 0. Now, when we have right triangles, we like Pythagorean identity, right? And we know already how wide this is. This is dx, right? We don't know the hypotenuse, but we want to know it. This side right here is actually dy. If this is the infinitesimal change in x, then this is the infinitesimal change in y. As you go from this point to this point, this is how much your x changes, this is how much your y changes, right? And if I know two sides, then I can automatically get the third. This squared plus this squared must be this squared, right? Yeah. Or this is the square root of dx squared plus dy squared. That's the length of that, isn't it? And I just need to add these up. The problem right now, as you might suspect, is that if I do an integral right now, it's going to start at A, it's going to end at B. That's pretty natural, right? We've been doing that. It'll go from A to B, but this formula, there's something that should be glaring at you, and you're like, whoa, we've never seen this before. What is the problem? What is that? Sorry? The dx squared. Yeah, hasn't every single integral we've done in this class had dx sitting out here? And this does not have dx sitting out here. And so that is a major issue. We need to resolve that. And it's going to be easy to do, but I need you to go back to Cal 1 and just think about something for a minute. All right. I mean, the setup is pretty straightforward though, right? Create this little infinitesimal right triangle, figure out its hypotenuse. So recall from Cal 1 some notation we had. If y is a function of x, then when we wrote f prime of x, we had another notation called Leibniz Notation, which said that we would write that as dy dx, right? Yeah. And I would like you to, I'm going to try and replace this dy right here. So I'd like for you to take that equation and solve it for dy. So just multiply both sides of this equation by this little dx, which we call the differential of x. So you're basically going dx here and dx over here. So you'll get f prime of x dx equals dy, right? All right, let's go back to this. Let's rewrite this, replacing dy with that, okay? So we needed that, but now we're going back to this formula. So this right here equals the square root of dx squared plus what? F prime of x times dx squared. Yeah? Now if you have two things multiplying and then you're squaring them, you can square each one, can't you? So this is going to become square root dx squared plus, let me write it this way, f prime of x squared times dx squared. So I'm just squaring each of these factors. And I just chose to use brackets so that I wouldn't get like parenthesis crazy here. All right? Now what do both of these have in common? They both have a dx squared, right? This term has a dx squared. This term has a dx squared. Factor out a dx squared. You get dx squared out front here. Then you'll have what? You got to be able to get that back. So 1, right? Plus, and then this thing. F prime of x, that quantity squared. That is what happens when you factor a dx squared out. Yeah? And because that's multiplication, you can split this into two roots. And what would the square root of dx squared be? Just dx. So we're going to get the dx to pop out. And this turns into square root 1 plus the first derivative squared. And then the dx, instead of putting it out front, I'm just going to put it back here because, well, it's about to go into an integral, isn't it? So we just usually put that dx out back. And that's it. That's our formula. So the length, if you like formulas, we have a nice formula for arc length. The length of a curve will be equal to the integral from a to b of the square root of 1 plus the derivative of the function itself, that quantity squared dx. There's your arc length formula. So it's a nice formula, but it's got some problems. We've seen in this class how challenging it can be to integrate square roots of things. In fact, we had an entire section called trigonometric substitutions, which helped us deal with square roots of certain forms. So this inherently is usually a difficult thing to compute, all right? It is usually difficult. Someone give me a function, just a common function. Like something, the first thing pops off the top of your head. What is that? What? X squared. I could probably do that. Find the length of it. Yeah, well, I don't know. It might be tough. X cubed would be tough, I think. Sine x would be tough. There'd be a lot. So my point is this. As the next examples I'm about to give you had to be very carefully chosen so that once you create this integral, you're actually able to do it. In general, it's not that easy to get these. So this is where we would use a computer to run an algorithm to get the length. But the computer needs series, and that's chapter 8, and we haven't talked about that. So, all right, you ready to find the length of a curve? All right. Y'all seem just overjoyed. All right, we start out easy. All right, let's find the length of f of x equals x to the 3 halves on the interval 0, 1. So we could have we could graph this on our graphing calculators and we would see what it looks like and, whatever. But we just want to find its length. And we don't need to draw any pictures, okay? For arc length, no pictures need to be drawn. You just can go straight to the formula. So what things will we need to do this? Square root of 1 plus the derivative squared, right? So why don't we just get the derivative first? Let's do some work first, then we'll go write the formula down. So what is f prime of x? We need that, right? This is derivative, not antiderivative, right? That's the good old power rule. Drop the 3 halves out front, subtract 1. That's your derivative. Now, within my formula, I need to square that, don't I? So we may as well square it now. If I take this and I square it, I get 9/4 x. Right? Because when you square, that 1/2 is square root. So when you square the square root, it goes away. All right. I think I'm ready. I think I'm ready to kind of go to the formula now and see what happens. The length of this curve should be the integral from 0 to 1, okay, square root of 1 plus the derivative squared, which I already did that work, dx. And now the question is, can you integrate that? How would you integrate that? So I'm going to do that over here. I'm going to write it down as an indefinite integral and act like I'm back in chapter 6 now. Actually, I don't even need chapter 6. How would you integrate this? Basic U sub. This is the good old, do you see something in its derivative? What's the U? 1 plus 9/4 x. Just grab the whole thing underneath the root. What's the derivative of that? 9/4. Just 9/4 dx. You don't have a 9/4, do you? But you have a dx, so I can get rid of this, scale it out, multiply both sides by 4/9. And now rewrite the integral. So if I rewrite this integral in terms of u now, it will be integral, let's see, this is square root of u. I'm going to write that as u to the half. And then what's dx? 4/9 du. So how about 4/9 out here? Du. And we can integrate that, power rule, right? So this will be 4/9 times, add 1 to that, we get what, 3 halves? So we put a 2/3 out front, u to the 3 halves, plus some constant. So it's looking like, what, 8/27 u, which is all of this, to the 3 halves. Yeah? That's our antiderivative. Questions? So I'm coming back over here now. I'm ready to finish this off. This will be 8/27 and then 1 plus 9/4 x to the 3 halves evaluated from 0 to 1. So that's the way we do definite integrals, right? You find the antiderivative, then you plug in the bar over here, and then you're going to go and plug in 1, then 0, subtract, and be done. Yuck. Let's plug it in. Who cares, right? Plug in 1, 9/4. What's 9/4 plus 1? 13/4. I'm just going to write this down. I've got 8/27. Then I've got 13/4 to the 3 halves, right? That's what I have when I plug in 1, which is a number, right? It's ugly, but it's a number. Then minus, what happens when I plug in 0? You just get 1 to the 3 halves, which is just 1 times 8/27. So how about just 8/27 here? And I'm going to box this and leave this as my exact answer. And I would take that on a test as full credit. I don't need the decimal. I prefer it to be in its exact form. Now, it would be interesting to see what that is as a decimal, because then you would have some idea, like, if it's like 1.756 or something like that. You have some idea of how